Welcome. We're going to get started with this afternoon's session. I am very pleased to introduce our keynote speaker, Vivek Wadhwa. He is an American technology entrepreneur and academic. He is a distinguished fellow and adjunct professor at Carnegie Mellon School of Engineering at Silicon Valley and a distinguished fellow at the Labor and Work-Life Program at Harvard Law School. He is also author of the books Your Happiness Was Hacked, Why Tech is Winning the Battle to Control Your Brain, How to Fight Back, Driver in the Driverless Car, Innovating Women, The Changing Face of Technology, and Immigrant Exodus. He is a commentator. You'll see him I've seen him on the news many times since we met. And he also writes a lot in the New York Times and other publications. So thank you, Vivek.
Thank you, Stacy. You know, at this conference, we've had a lot of detailed coverage about what's happening today. I'm going to take you a little bit into the future, but I'll tell you what's going to happen in the next 5 or 10 years, and why we're now reaching a tipping point in which we'll be able to cure almost any disease. Let's start by going backwards a little bit. Do you remember this, the Apollo mission?
Roger, tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're going to be busy.
Armstrong is on the moon. Neil Armstrong, 38-year-old American, standing on the surface of the moon. On this July 20th, 1969.
That's one small step for man, one giant leap for mankind.
Why did I take you to 1969? Because I wanted to show you what the technology behind this was. We marveled at what took us to the moon. It was a feat of technology. The technology was this, the Apollo guidance computer. In technical terms, it was 2.048 megahertz. In simple English, it had the same computing power as today's musical greeting card. That's what took us to the moon. That's what we were marveling at for the last 30 or 40 years. And today we're marveling at these beautiful images we're getting from Mars, the NASA rover Curiosity. You know something? That's a 2-megapixel camera we have up there. 2 megapixel. Those old cameras we threw in the garbage about 10 years ago. It's got 1/6 of the processing power in an iPhone. That's what we're marveling at. Technology is advancing exponentially. This is its history. It took thousands of years to go from agriculture to pottery to the plow to mathematics. Over the last 100 years or so, we've had advance after advance after advance. We don't seem to understand exponential because it's happening so fast, and we can't perceive this pace of change, but this is how technology is advancing. Let me simplify this a little bit. This is what you get for $1,000. This is Ray Kurzweil. Ray Kurzweil is considered to be one of the greatest futurists of our time. He put together a computation on where computing is taking us. As of 2010, for $1,000, you got the computing power of a mouse brain. By 2023, which is what, 4 years from now, those $1,000 devices you buy will have the same computing power that your brains do. We stop. We're not getting any upgrades, but the computers keep getting faster and faster and faster. By 2050, the $1,000 device will have the same computing power as every human being on this planet. What does this mean? No one really knows. The only thing we know is that this is happening, and it's not only computing, it is everything that computing touches that is advancing exponentially. AI, robotics, 3D printing, virtual reality networks, sensors, digital medicine, you name it. Practically every technology which becomes information goes on this exponential path. I'm going to show you a couple of these technologies to illustrate, this pace of change, because we have a very hard time understanding it. Let's start with our good old robots. Do you remember her?
Hello. I'd like to rent a maid.
Rosie!
Coming, sir. Here I am, sir. Here it goes.
R2-D2, a pleasure to meet you. I am C3PO Human Cyborg Relations. I beg your pardon, but what do you mean, naked? My parts are showing. My God.
These are the robots we grew up dreaming about, and we thought when we grew up we're going to have R2-D2 and as our, and 3CPO as our friends, and Rosie serving us. And we grew up, and what did we get? These clowns over here. It's the 2015 DARPA Challenge, the best and the brightest. So this is why we're so skeptical. We don't believe technology can move this fast. So now let me take you through in slow motion what happened over the last 20 or 30 years. Start with this, with Carnegie Mellon University, which is where I teach. It's the leg lab. 20 years of progress we're watching. 20 years of progress. All right. They were very excited, but big deal. The founders of the leg lab left CMU and joined a company called Boston Dynamics. And watch what they did over a 6-year period. Now watch what happened over 4 years. It's pretty darn good, isn't it? Now these humans can't stop hitting the robots, but that'll fix itself. Now watch what happened over 2 years. So we went from 20, 6, 4, now to 2 years. Watch the progress. No one's going to mess with him. And then watch what happened over 1 year. It's pretty good, isn't it? What happened over here? Computing and AI advanced exponentially, and as I showed you earlier on. And then we had sensors and cameras and actuators advanced at exponential speeds. The cameras you have in your smartphones are more powerful than what Universal Studios had 20 years ago, 15 years ago. I mean, high definition images you're taking on your cameras, these videos, they're better than what the film studios could do. We don't even realize the power we have in our pockets. All right, now let's look in our pockets again. What you have there are advanced accelerometers, gyroscopes, moisture sensors, proximity sensors, barometers, touch screens, technologies that would have cost hundreds of thousands of dollars and weighed hundreds of pounds just 30 or 40 years ago. You have better technology in your pockets than we have in our nuclear missiles right now. The guidance systems in your pockets are accurate. So when you launch Google Maps, it can tell you exactly where you are and guide you. Right? This is how the technology is advancing. And then AI. What is AI? We keep hearing about artificial intelligence. Well, AI is all of these things, everything from Siri to the self-driving cars to the stuff we saw in science fiction. This is all AI. And we've been hearing about AI since we were kids as well. I mean, go back to 1958, my university, you had scientists predicting that within 10 years we're going to have chess champions that beat human beings. Machines will be able to do what human beings can do. We've had this over and over and over again since we were kids. And what happened? Nothing. Great expectations dashed hopes. And then what happened? The Japanese decided to spend billions of dollars on this, and their project failed. So everyone thought that AI was dead. AI didn't die. AI was born again because the methods of programming AI changed. Instead of writing if-then-else statements like you do in computer programs, they said, why not mimic the human brain? The human brain doesn't have if-then-else statements. You don't program the brain. The brain learns through neurons. You have connections between them, and the weights change depending on what you've learned. So scientists said 30 or 40 years ago that maybe that's a better way of doing AI. The trouble was, to build these neuron-based processors, you needed supercomputers. Supercomputers were extremely expensive, and they were huge. A supercomputer would fill this room. So as I showed you, the computers became much faster, but we still didn't get parallel computing is what you needed. And then what happened? Our kids started playing video games. So a whole bunch of companies such as NVIDIA started seeing opportunity in building what are called graphic processing units to make the video games faster. And the scientists saw this technology and said, oh my God, these are massively parallel computers. Why can't we use them for AI? The answer is you can use them for AI. And then we started gathering massive amounts of data. And then they developed better algorithms, better methods of analyzing the data. And the magic happened. AI is now everywhere. It's in our air traffic control systems. It's in the software you use. Wherever there's data now, there's AI. And what exactly is AI? AI is a method of analyzing data. You know, there's a lot of hype about AI. What we have today is what's called narrow AI, weak AI. You essentially give it lots of examples. You say, look, this is a duck, this is not a duck. A duck has a beak, it has the wings, it has these features. You give it enough examples of that, and the computer associates a pattern, that it's something that looks like a duck with a duck. And when you say, is this a duck? It says, yes, this is a duck. That is artificial intelligence today. So don't be fooled by all the hype you're hearing, all the buzzwords that the techies put out. It is simply pattern recognition, and it needs lots and lots of data to be better. But when you give it data, it's amazing because AI remembers, computers remember everything you told them. We forget. AI remembers, and it keeps building on what it learned before. This is where we are today, narrow AI. And then the next step, for this we almost require some magic to happen because we're nowhere close to this right now. It's the stuff of science fiction, artificial general intelligence, AGI. When the system decides what it wants to learn on its own. When it starts inferring what it sees and gains human-like knowledge. We are nowhere close to this. Because once you have that and you have the supercomputers I talked about in your pocket, you get the craziness that Elon Musk and Stephen Hawking and others have warned about, which is superintelligence. So don't worry about that. AI is simply better data analysis. That's all you need to know about AI. So when people say AI, you can laugh at them, say, I know what that is. It's data analysis. Now let's look at medicine. Let's make it personal. Apple is now in the medical diagnostics business. That's what the Apple Watch is. It's a medical device. Apple, over the next year or two, is going to be releasing a whole new set of medical sensors because the technology industry has realized that the next big market for it is the medical industry, a $3 trillion industry. And it's now getting into the game, which is a wonderful thing because the tech industry is going to disrupt everything using the tools that they have. So this is wonderful. Next step, you won't need iPhone cases. You won't need these peripherals. We're essentially going to have sensors on our bodies that monitor us 24/7. You know, that Fruit of the Loom tag on your underwear or, the coats that you wear, they're going to have sensors in them which monitor you. Your shoes will be monitoring your activity levels, uploading it to the cloud 24/7, gathering all of this data on you. And then going inside the body. Already there's several products that go and navigate inside the body. The technology is getting better and better and better. There's still limits to where you can go in the body, but scientists are developing these new navigation systems by which you can go anywhere and deliver medications precisely where they're needed or do surgery at the nano level, at the smallest level. This technology is being developed. Do you remember the movie Fantastic Voyage? In which they shrunk those human beings, put them inside the shrunken submarines, and then they explored the body? Forget the shrunken human beings. The bad news is we're getting bigger, we're getting fatter. We're not getting any smaller. But the shrunken submarines are just about here. And it'll be amazing what becomes possible with these technologies. So we're gathering massive amounts of data. Data. What did I say you do with data before? You use AI to analyze it. And soon, when I say soon, in the next 5 years or so, in almost every field of medicine, we would have gathered enough data so that AI is better than our doctors are. Our doctors can only process so much information. AI can process massive amounts of information and diagnose disease and symptoms better than human beings can. This is coming in the next few years. And there are going to be apps on your smartphones which are your daily assistants, your doctors who are guiding you. And then there's the human genome. In the year 2000, there was a race between the US government and a scientist, Craig Venter, to sequence the human genome. The government and affiliated labs had spent $2.75 billion. The scientist, Craig Venter, came up with about $100 million. He took government data, and he beat the government to the punch. It made front-page news worldwide that we had been sequenced. It was a big, big, big deal that the human code had been deciphered. What cost $3 billion in the year 2000 costs roughly $500 at the low end today. At the rate at which this is progressing, within 3 or 4 years, we'll have iPhone cases or USB drives that do complete human genome sequences. Within 5 or 7 years, it'll be cheaper to get a complete human genome sequenced than to buy a cup of coffee at Starbucks. This is how it's going. And this opens up incredible possibilities. It also means that we've become data and our doctors are becoming software. This transformation is now in high gear. Now let's talk about using all of this to cure disease. What exactly is disease? Well, disease has a bunch of symptoms: cough, fever, abdominal pain, rashes, etc., etc. It's caused by genes and proteins. The medical industry focuses on symptoms. This is what Western medicine is based on, is curing symptoms. However, the treatment may be at a molecular level, and it may be at the holistic level, at the whole body level. So let's walk through what's happening here. This chart over here shows you what's called the Human Symptom Disease Network. You know, there are only about 300 or 400 symptoms altogether. I mean, yes, you have a pain in the butt, you have a cough, a cold, there's only so many things you can complain about, right? And there are a finite number of diseases. So this study looked at the vast majority of the papers published in this area, and what they determined was that there are 150,000 connections, roughly, between all of these. Now, for a human being, that's very hard to comprehend, but for an AI, that's baby stuff. So understanding disease is a job better done by AI than by human beings. Now let's talk about cancer, which is near and dear to our hearts, because it is the leading killer worldwide of human beings. Cancer isn't a single disease, it's a bunch of DNA mutations. Every cancer is as unique as we are. Every cancer that every person has is different, and it keeps changing, it keeps mutating, and that's the game it plays with us. It outsmarts our body and its defenses. So the traditional treatment for cancer has been the nuclear option, that you drop a nuclear bomb and you radiate, or you do chemotherapy and you stop the cells from replicating. This is how we've done it so far. Now there are targeted therapies. So you're attacking at the molecular level. You're now either blocking signals, or you're changing proteins, or you're inhibiting blood vessels, triggering the immune system. There are different techniques for targeting at the disease level. And the beauty of genomic sequencing is that it allows us now to recognize the cancer. And the message that the Cholangio Foundation has is that mutations matter. Mutations matter because now we can strike the cancer based on the protein expression and mutation instead of the location and type. It's no longer a matter of what type of, is it a liver cancer, is it a throat cancer, is it a, this cancer, that cancer. It's really now a matter of attacking it at the molecular level based on the genes. So this is state of the art today. Mutations matter. Let's move forward now. This is how the body defends itself. This is what's called the immunity cancer cycle. This chart is by Dan Chen and Ira Melman of Genentech. What happens is that when a cell starts mutating, it releases proteins that are called antigens. You have defense mechanisms in the body. You have these sentries, I mean, these night watchmen that go around looking for trouble. When these dendritic cells, when they see trouble, what they do is they take a sample of the antigen and they take it to the soldiers, the T cells. The T cells are the warriors. It basically turns them on and says, okay, go kill. And the T cells travel to the tumor, and then they infiltrate it and they kill the tumor. This is the way it's supposed to work. Now, in this process, there are many stimulators and many inhibitors. At this conference, you had heard all sorts of buzzwords. You heard people talking about different parts of the cycle, and you have different companies attacking different aspects of it. The researchers are attacking different aspects of it. They're focusing on, for example, chemotherapy attacks at step one when the cell goes bad, so they try to kill the cells. Other drugs try to go to a different part of the cycle and start attacking it. So this is why you hear all these buzzwords that you don't understand. Just like in the tech industry, they try to confuse everyone by throwing fancy words out. This is how, the techies preserve their jobs. The same thing happens in the medical industry, that they use all these fancy buzzwords, and they live in their own domains and use all these fancy words. But this is essentially what they're doing, is, going to a different part of the cycle and trying to address it. So you have checkpoint inhibitors, for example, which now block a defense mechanism that the tumors use by expressing a protein. The protein PD-L1 says, hey, I'm a friend, don't attack me. This is a trick that the mutant cells use. So what the inhibitor does is it disarms it. It says, nope, you're not going to get away with that. And therefore, your T cells can kill that cancer. And then you have the T cell therapy, the adoptive cell transfer. In this, what you do is that you take the T cells from the body, you take the tumor, you sequence it, and then you find the antigens that the T cells can attack. You clone them, you produce billions and billions of them, just like what happened with Melinda, and then they go and they do their job and they kill off the cancer. The trouble is that when you're attacking antigens, you can also attack healthy cells. You have these things called cytokine storms, and then there are barriers. I mean, first you have to identify the right antigens. For cholangio in particular, it's hard to identify those antigens because there hasn't been much research done yet, because there hasn't been enough data yet. I say yet, it will be solved. So if we could identify all of these antigens, we could now start training the killer cells, the T cells, to go in and clean up and fix the immune system. But there are problems with this technology because of the lack of information. And now you have personalized vaccines as well, which work at what's called the neoantigen level. Neoantigens are more specific antigens, which are only expressed by cancer cells. So the problem I talked about with the T cells attacking antigens, they're reduced because these are only on cancer cells. So with this technology, what they're doing is that they're identifying those neoantigens, and then they're creating the equivalent of a vaccine and injecting you with the vaccine and curing it. The trouble is that it's hard to find these neoantigens. For some tumors, they found them. For solid tumors, there's less data out there. Now, in cancer, what scientists are discovering is that 1 + 1 = 3. That, I showed you that chart which you had all of these different cycles. So rather than just attacking one of it, if you start attacking multiple points of entry, multiple weaknesses, you can be a lot more effective than you could just with one drug. This is why a lot of these clinical trials you're talking about, they're combining different drugs. So that's the way the system works. By combining drugs, you get more effectiveness. Now, here's what the problem is. That I showed you that complex chart of, of all these interactions and all of this whole cancer life cycle. You have drug companies that are focused on particular nodes on that cancer cycle. You have researchers who are trained only within one specific technology. To be able to cure this cancer, you have to be able to understand the whole picture. And that's not how the system works. So the drug companies fund research that the academics do, and the research is focused specifically on the drug that the pharma company is producing, plus another one that they want to match up with. So the wild experiment, for example, what Helen Scott talked about, taking off-the-shelf drugs meant for completely other purposes, generics, and applying them to the tumors. Maybe they do work, but no one is researching them because there's no money to be made in it, and the researchers don't have the funding to do that. This is what the problem with the system is. You know what this is like? The tale of the wise men and the elephant? They're all looking at different parts of it and thinking that they know everything. So this is what the problem we have today. Now, there is hope. My hero in immunology is Sean Parker. He's a friend, and what he's doing is absolutely incredible. He made a lot of money at Facebook and Napster and so on, and he's taken $250 million to found an institute that's bringing researchers together from all over the world and causing them to share data and work together and to look at the big picture. So there's a lot of hope because we have people now who are looking above it all, who can see the big picture. And he happens to be a tech guy. So the technology people seem to understand the value of looking at the big picture and doing different things. So this is exactly what the Parker Institute is doing. And I'm a big fan of theirs. And Sean is a friend, so I respect him for what he's doing for the world. Wonderful, wonderful human being. All right, next. So I talked about, what comes after, the targeted therapies. There's another frontier which is about to upend the entire basis of Western medicine. It's the microbiome. When you went to school, your teacher taught you that the human body is made up of cells. The cells have a nucleus. That's where the DNA is stored. Guess what? Your teacher was wrong. We're not made up of cells. We're made up of bacteria. There's somewhere between 2 and 10 times more bacteria in our body than there are cells. We are a cocktail of living organisms that seem to be doing all the dirty work and the good work. Let me walk you through some studies to show you what's being discovered. There have been several research papers published now in which they took the feces is the polite way of saying shit, feces of a fat mouse and gave it to a thin mouse, and the thin mouse gained weight. They took the feces from a thin mouse and gave it to a fat mouse, and the fat mouse gained weight, and the fat mouse lost weight. The Chinese replicated this in human beings. So what am I saying? That you lose weight by eating shit? I mean, that doesn't make sense, does it? Watch this space, because it seems that the microbes you have in your body may be a determinant of your obesity. Crohn's disease, a debilitating disease that children get. By doing fecal microbial transplants, they were able to remove all the symptoms. There have been several studies with several diseases in which they transplanted fecal matter from one person to another. It produced amazing results. Antibiotics can be lifesavers, but they're used to excess. And what it seems is that when antibiotics are used the way we're using them, they also cause obesity. So there have been studies that show that children who received antibiotics tend to be obese. There's research that shows that microbes may actually be turning genes on and off. They may be programming the genes in our body. And it may also have a direct impact on cancer. There's several studies now which show the relationship between the microbes and the efficacy of immune checkpoint blockers and all sorts of other diseases. A lot happening here. Watch this space. And this is why you have a lot of patients who are now trying healthy foods, who are trying different types of probiotics, and they're showing amazing results. Not enough research here yet. It'll happen. Now let's talk about diagnosis. I'm going to take you to India to show you the future of diagnosis. That we're fortunate to be in America and to be able to get diagnosis. You can go to a hospital and get blood tests and whatever you need. In the developing world, in the rest of the world, you can't do it. Billions of people don't have access to healthcare. And when they do, they can't afford it. So this device made in New Delhi is called HealthCube. It does the same tests that are done in hospitals, everything from blood temperature, grouping, hemoglobin, HIV, dengue, malaria, 12-lead EKGs. Watch this. The problem here is it takes 2 to 5 days to get diagnosed for regular diseases, and then people drop out of the system. Let's go to New Delhi to see this in action.
At IDEA, we have evolved the social entrepreneur model, embedding the health cube. We are able to reach out to rural areas, including labor migrants, and offer them a path to proactive wellness. Timely health screening and diagnostics on 32 related tests, including all pathological tests, blood sugar, hemoglobin, blood pressure, and many more issues are diagnosed before they turn into a major illness. We have created an army of village social entrepreneurs who do the health screening at a very nominal cost. We have taken HealthCube to Haryana, Uttar Pradesh, Kerala, and Andhra Pradesh, collectively spanning 20 districts and 100 locations. In all these, we have seen a palpable change, healthier people, fewer illnesses, and a general sense of well-being.
I have a HealthCube at home. I can do my own cholesterol tests, I can do my own 12-lead EKGs, I can do tests for dengue, malaria, pregnancy, whatever we need to do, we can do at home. You know what the device costs? $1,000. You know what? Each test costs 30 to 50 cents. Now, this is the future. I'm on the board of this company. I invested in it. I got involved on one condition, that we take this to the developing world before we bring it to the West. Because billions of people need to get it before we do, because they're dying. And if we brought it here, the medical establishment would feel threatened by it, because we would have access to our own data. I get my results immediately, instantly on my smartphone. I have all my medical records, all these diagnostics on my smartphone. So the latest version of this does 100 tests. Imagine adding to this all of the other diagnostics, having spectrometers and being able to do next generation sequencing on your phone, having it available to you immediately, and then calling up a doctor anywhere in the world and getting advice immediately. This is the near future. It's already happening outside the United States. Now, I'm going to conclude with a simple message. Every technology can be used for good, and it can be used for evil. I worry about the dark sides of technologies, because everything, good seems to turn dark, like we're seeing with social media and a lot of other things. We right now have a choice between these two futures.
Space.
Mad Max and Star Trek, and both at the same time.
Starship Enterprise.
If you look at the dire state of affairs in country after country, and if you look at the amazing things I'm talking about, they're happening concurrently.
A new civilization.
So what we have to do right now is we have to make some really difficult decisions with every technology. Does it have the potential to benefit everyone equally? With HealthCube, I chose to invest on the condition that we take it to 1 billion people before we bring it to Americans and Europeans. Why? Because if we leave them out, then we get the darkness of Mad Max. Instead, let's benefit from having helped billions of others. And then do the rewards outweigh the risks? I didn't cover many other technologies. I could have covered a lot that I'm terrified about. And then does it promote autonomy or dependence? I suggest you read my book, Driving the Driverless Car, because it walks you through this future and tells you about these technologies and the choices we have to make. But the bottom line is that I believe we can build Star Trek, that I believe we will be now curing disease and exploring the heavens. I believe that this future that we dreamed about is going to happen 300 years ahead of schedule because of these advancing technologies. It's not going to be easy. There are a lot of problems along the way. The future is not equally distributed. Some people are going to get it before others. But at the end of the day, we will all benefit from this. Thank you, everyone.